a page. The size of page table is greater than a page. So look, there are very interesting issues. The first thing is where to store the page table. So you cannot store it on cache or onboard. Onboard means on chip memory, onboard memory, because size is bigger. So it is not possible here. So obviously page table will be stored in main memory. And main memory is already, as we know in paging architecture, main memory is already divided into equal size frames. Now the question here is, if your page table, and this page table is also going to be stored in main memory, which is divided into frames, and if it is bigger than a page, and you know that the page size is equal to frame size. So your virtual address space and physical address space is divided into equal size partitions, which is known as page in virtual memory realm and frame in physical memory realm. So if your page table is bigger than a page, means it can have many pages. So you have to page the page table also. That was the concept we were discussing. And I told you that there are two possible solutions. One is inverted page table, which I asked you to go through. Another is multi-level page table. Multi-level page table. So I'll give you some hint regarding multi-level page table. Today, inverted you go through by yourself. Okay. Now there is one more thing which is there in modern operating system and processor, which is known as segmentation. Let me take the snip of this. Now this is more aligned with the, you can say, the vision of a programmer. The concept of segmentation is more aligned with the vision of a programmer. Programmer never think of their programs as existing in one continuous linear address space. Yeah, they think of memory in multiple segments. Fine, and that's how architectures are also developed. Like if you talk about x86 architecture, so we always talk about in terms of code segment, data segment, extra segment. So we think about, when we develop a program, we say that there is a one segment, another segment, which may be of unequal sizes. So they tend to think of their memory in multiple segments, each dedicated to a particular use, such as code, data, stack, heap, etc., as we have seen in our x86 memory layout. Segmentation actually supports this view by providing addresses with a segment number. And these segments can be of unequal sizes. And how to access to a segment? You just need to know the base address of the segment, from where the segment is starting, and the size of the segment. And then you can convert your virtual address to actual physical address where segmentation is happening. So there are two different ways of converting virtual address to physical address. One we have discussed, that is paging, which is more popular in operating system and architecture, where you divide your main memory into equal size frames and virtual memory into equal size pages, and then you map page to frame. If your architecture and operating system together are supporting segmentation also, then it may so happen that your virtual address is converted into some segment number and the size of the segment or offset into that segment. So this, how this is getting done, that's what we are going to see. Let's see. So logical address consists of two tuple, segment number and offset. So in your view, your virtual address, you think of virtual address as segment number, and within that segment, what is that line number or the offset? Now, what is going to support you to translate this segment number and offset, which is of virtual address, into actual physical address? There is a segment table where this two-dimensional physical address, each table entry has base containing the starting physical address where the segments reside in memory, and limit is the length of the segment. As we have page table base register, we have segment table base register, which points to the segment location in the memory, segment table's location in the memory. Segment table length register indicates the number of segments used by a program. Obviously, your segment number S is legal if S is less than STLR. So similar to our paging, we have segmentation, but treatment is different. So in paging, what you used to do, your virtual address consists of two things, page number and offset within that page. Here your virtual address is going to be having segment number and offset within the segment. In paging, there is a page table, and when you load a process, the PCB contains the base address of the page table. Fine, where the page table of this, just a minute, I have to take this call. Class. So in segmentation, your virtual address is having two parts, segment number and offset. And then we have a segment table. Again, the base address of that segment table is there in PCB. One more thing is there, the length of the segment table also, because now different segment tables can be of different sizes, because depending upon, because segments can be of unequal size, depending upon how many segments a process is using, your entries are going to be there. So segment table length register is also there, which controls the base and limit of segment table. Within a segment table, what is there? Just see. Within a segment table, there would be base of the segment, that segment, and limit of that segment. So just please don't get confused. When you load a process, PCB will give you segment table base register. PCB will be having segment table base register where the segment table can be stored, and this particular value would be stored in a register of a processor, STBR, segment table base register. And from there, you can get an idea that in main memory where the segment table is there. Then from PCB, we can get the value which has to be fed into segment table length register, which is going to give you the size of the segment table. Within the segment table, there would be base and limit again. So means this segment number, virtual address segment number, is going to be found out in some base where that segment starts and what is the size of that segment. So this is how segmentation supported architecture and operating system. This is how the translation is getting performed. How it is getting done, you can see here we have, let me take the SNP. You can see CPU generate a logical address having segment number and offset. You go to the find this segment number, index into this segment table. You can get the limit and base. So base address means from where this segment is starting. You go to here, and using this limit and this offset, you compare limit with the offset. If this is offset is less than the size of the segment, then you add this offset into the base and you get the physical address. If not, then it's an addressing error or the segmentation fault, which you actually might have experienced. Just example here. So logical address is space, segment 0, 1, 2, 3, and 4. Segment 0 starts from 1400 and limit is 1000. So this is how these segments are stored in main memory. Fine. Like segment 0 is starting from 1400 and going size is 1000. So 1400 to 2400. Segment number 1 is starting at base address is 6300 and size is 400. So 6300 to 6700 segment 1 and so on and so forth. You get the segment number, go to the segment number, get the base, you get the starting address of the segment, you compare this limit with the offset, this D. If offset is less than this limit, obviously you'll add this offset into the base address and you'll get the physical address. This is how segmentation is performed. Fine. Any questions from anybody? Abhigyan, any questions?
Yes.
Brijendra?
Yes, sir. So for every processor, there is a separate segment table.
Obviously, for every process, like when a process loads, fine. I told you, process creates so many things.
Yes, sir.
So when you, that's why when we create a process, that is a state, not an event. Remember?
Yeah, it is a
Embryo,
state. Yes, sir.
embryo, no? When we say
Yes, sir.
new or embryo. So new and embryo, why it is a state? Because when you want to create a process, obviously you fork some process and then you change all those things, do the exec and all. So you need to create so many other things also, and page table and segmentation, depending upon the architecture you are utilizing, page table and segment table is one of those things. So you need to initialize the page table also. So where the
Yes, sir.
page table is going to be stored, that is going to be told by the processor register, which is page table base register. The address, the register CR3 in XV6, remember, in
Yes, sir. Yeah,
x86. So that is going to tell you every time when a process starts, it creates a virtual address. Virtual address will look for CR3. CR3 value will give you the page table base register, and then there you find the page table in main memory. Fine, and then
yes,
you go and index into page table to get the frame number. Similarly, if segmentation is supported, so you will get the base segment table base register. There would be a segment table base register. And from there you get the segment table location, and then there you, so you, every process or every process is going to have a separate segment table. That is not a complete sentence. When a process runs, it requires a segment table. When process is not running, fine, it may be in main memory, it may not be in main memory. Are you
yes, sir.
getting my point or not?
Yes,
So
yes.
that segment table, what is segment table? Segment table gives you this segment in main memory where it is available.
Yeah, it is the only thing. Yes, sir.
So just look at the whiteboard here. Now suppose at time t naught, when you brought back the process P1 from hard disk to main memory, suppose if this is main memory, the process will be trying to get the space. So first of all, you need to populate the page table. This process might be having, say, 30 pages. It's a big process which might be going to accommodate in 30 frames.
Yes.
So you will never bring the whole process. The first thing what you need is bring the initial page for which the page fault has occurred. Are you getting my point?
Yes, sir.
Suppose you scheduled a process P1, fine, and that is in hard disk. I'm giving you the whole scenario. Just please be with me. Everybody should be with me. Suppose a process was running, P1 was running on processor. This process went for an IO. Fine. Please mute. Somebody is unmuted. This process went for IO. Obviously, when process goes for input output, this P1 will leave the processor. Okay, okay, Brian. Now,
Yes, sir. Yes, sir.
now P1 in goes to ready queue. Okay, and it is waiting for this IO event to be completed. Okay. Now this, it may happen, and normally it happens that P1, P2, P3 all ran on processor for some time and all are waiting for IO event. Okay. Now what you need to do, after some time, the ready queue would be exhausted. So what you will do, even if P1 is waiting for some IO event to happen to complete, P1 would be swapped out to bring more ready processes into ready queue so that they can execute. Is it okay? Now
Yes. Yes.
P1 from processor to ready queue in main memory went to hard disk and waiting for IO. Okay. When it went to hard disk, all the pages also there on the hard disk. So memory is reclaimed by another process which are running currently. After some time, this IO event will be over. You get the interrupt. OS will get the interrupt. OS searches for P1 in ready queue. Okay. Will not find it. It will bring the process into main memory. Where in main memory? So OS will be having list of empty frames. Fine. So OS, first of all, try to populate the page table. So OS suggested, so from here I will store the page table for this page. Okay. For page table for this process. OS will populate the PTBR. Getting my point? Okay.
Yes, sir. Yes.
This everything will be done. Now process will be there in main memory. One page of that process. Fine, one page of that process. Which page? For which that IO event, for which that line of code, the IO event has occurred, from where the process has stopped. Getting my point or not? Okay.
Yes, sir. Yes, sir.
And in page table, that particular frame would be populated. So you start executing the process. Suddenly you require another page which is not in the main memory. that would be a trap to operating system. Operating system again goes to hard disk, bring that page into main memory somewhere, update the page table, and restart that instruction. Getting my point or not? So every
Yes, sir.
time P1 runs, it may so happen that it has to brought back from the hard disk, and it may run at different places in main memory. Every time P1 runs, its page table may be stored at different places in main memory. Because it is not sure when P1 is running at time T0 and P1 is running at time T1 and P1 is running at time T2, it is going to run at the same memory location. No, we have runtime address binding. Okay. So for that
Yes.
purpose, we have to have a page table. So where P1 is stored right now, where pages of P1 is stored right now, that will be told by page table. Page table also stored somewhere every time different place. Where the page table is there, for that purpose we have a definite register, definite memory, page table based register. तो शुरुआत यहीं से होती है. प्रोसेस चलेगी, उसका पीसीबी आएगा, ठीक है. पीसीबी ढूंढेंगे, सबसे पहले देखेंगे कि पीटीबीआर की एंट्री क्या है, ठीक है. पीटीबीआर
Yes,
को
yes.
ढूंढेंगे तो पेज टेबल मिलेगा, पेज टेबल मिलेगा तो पेज मिलेगा, पेज मिलेगा तो फ्रेम मिलेगा, एंड फाइनली इंस्ट्रक्शन को हम एग्जीक्यूट करेंगे सीपीयू मिला के. गॉट द पॉइंट?
Yes, sir. Yes, sir. Got the
And
point.
same thing is happening with the segment table also. Okay?
Yes, sir.
Abhigyan, is it okay?
Yes, sir.
Fine. How do we protect the memory using paging? And this is interesting. So we can add a bit or a group of bits to the page table entry. And to classify a page as read write, read only, read write execute, you can use this bit or group of bits. Whether this page is readable only or we can write into that page. And then you can check each memory reference and see that whether that memory reference is in appropriate mode or not, depending upon what you have allowed to do that. Now, you can also have this arrangement valid or invalid, which can be used to mask off the entries in the page table that are not in use by the current process. So if certain page entry is invalid, means अभी तक इस process ने इस page number का use नहीं किया. अगर use किया है तो invalid को पहले valid करना पड़ेगा. This is how we can add some more bits into page table to do some more protection or mask off some entries and things like that. Page table size, as I told you, suppose the size of logical address space is 2 to the power m bytes and physical memory is 2 to the power n bytes. Obviously, logical address would be m bits long and physical memory address are going to be n bits long. Suppose the size of each logical page and physical frame, because they are equal, frame size and page size is equal, is 2 to the power k bytes. So as I told you, most significant m minus k bits indicate the page number, and least significant k bits will indicate the offset within the page, which byte of that page you are. So there would be 2 to the power m minus k page table entry. That's what I'm telling you. You can see here at the whiteboard that 2 to the power m is virtual address size, 2 to the power n is physical address size, 2 to the power k is page size. So your virtual address would be m bit long. Your page size is k bit long. So m minus k would be the page number. So how many entries are going to be there in the page table? 2 to the power m minus k. 2 to the power m minus k page table. Where each page table entry stores the physical frame number, and some other things if you include valid, invalid, or another protection bits. So in any case, each page table entry is going to store physical page number. Physical memory size is 2 to the power n. So every entry is going to store n bits plus some bits if you are including valid, invalid bit or any other protection bits. So using this information, we can get the size of the page table. Using this information, we can get the size of the page table. So there are total to the power n minus k physical frames. Take n minus k bits to identify a physical frame. Sorry, it would be uh, n minus k bit because k is the size of frame also. So physical address would be of n bit long, each frame is k bits. So how many physical frames are going to be there? N minus k. So every page table entry would be having n minus k bits plus some additional bits. So each page table must be at least n minus k bits in size if you exclude all other information. So the total size of the page table is at least to the power m minus k into n minus k bits. Note that PT contains a bit more information than just the physical frame number, like permission to access the page. So page table entries are slightly longer than n minus k bits. So you need to see this, and if you get any numerical like this, that how many entries are there, how many extra entries are there, you need to take care of that to calculate the size of the page table. There are different implementations of page table. If you talk about modern computers, they support logical address space of 2 to the power 32 to 2 to the power 64. With 2 to the power 32 address space and like 2 to the power 12 page size, this 2 to the power 20 entries are going to be in the page table. 4 bytes per entry amounts to a 4 MB page table. Now the page table is too large to reasonably keep it in contiguous memory. If you have 4K pages, size pages would take 1024 pages just to hold the page table. So there are solutions like hierarchical page table, multi-level page table, inverted page table, you have to study yourself, and hashed page table. It's very interesting idea. You have to study yourself. When I say study yourself, you need to study. This is mandatory because 1 or 2 questions may be asked on that. So what I was trying to tell you that if there are 2 to the power 20 entries and 4 bytes per entry, because page size is suppose 4K bytes, then your page table itself is of 4 MB and frame size is 4K. So you require 1024 pages of page table. So you need to do something to just have a solution for that. So hierarchical page table is most logical and most used ones. There are another 2 techniques, inverted page table and hashed page table, which you need to study by yourself. 2-level page table, just example. Suppose a logical address on 32-bit machine with 4K page size is divided into page number consisting of 10 bits and a page offset consisting of 2 to the power 12 bits. So 4K means 2 to the power 12, 2 to the power 30 is the total virtual address. So 20 bits would be there in the P part. Fine. Now since page table is page, the page number is further divided into 10-bit page number and 10-bit page offset. So जो 20 बिट है उसको भी डिवाइड कर दिया. 1024 पेजेस हैं. किस पेज की बात कर रहे हो पेज टेबल में? उस पेज टेबल में 1024 एंट्रीज होंगी. किस एंट्री की बात कर रहे हो? एंट्री मिल गई तो वो फ्रेम नंबर मिला. उस फ्रेम में किस लाइन की बात कर रहे हो? So analogy is page table is kind of a book. Fine. Page table is kind of many pages of page table. So when I say P1, P2D, where PD was single level page table, page number you index into the page table, you get the frame number and then offset. Here the first will be which page of the page table, this one, this one, this one, or this one. Suppose this page. Then P2 is going to tell you which entry of this page. Then you get to that entry, you get the frame number, and then you attach offset into that frame to get the which line of that frame. This is how a multi-level page table. We can have multiple levels also, which we can have P1, P2, P3 also for three level page table. Fine. That which shelf, if it is a three-level page table, which shelf P1 is going to tell you which shelf, P2 is going to tell you which book, and P3 is going to tell you which page. Fine. So depending upon the size and the of virtual address space and size of your page, you can have multiple level of page table. Fine. Rajendra, any problems?
No, sir.
Okay. Two level page table as that outer page table. Fine. And then you go to that, and so P1 is going to tell you the outer page table. This is going to tell you which page of the page table, and then which line of that page is going to be told you by D. In this way, we can have multi-level page table. Now, this is most interesting, which we have already discussed when I was discussing XV6. Now, see here, this is the situation where many people get confused. Now, if I ask you a question, everybody should listen carefully. Brajen, you also. Suppose there are process P1 and process P2. Fine. Whether the virtual address of P1 and P2 can be same?
Yes,
Virtual.
sir. It can be same.
Okay. Now the another question is, can physical address be same? Yes or no?
No, sir. No, sir. Otherwise, it will override the data.
So you are saying no. Anybody else? Abhigyan?
No, sir, it cannot be same.
So how we have access the kernel of XV6? Now remember, XV6 process management lecture. We have only one copy of kernel code in main memory, physical memory. Remember, Brijendra?
Yes, sir. It is having only one copy.
One copy. Means, and many processes P1, P2, P3, all will go to the kernel mode.
Yes, sir.
Kernel mode means what? From user space to kernel space.
Yes.
And I told you at that time that it is very easy, because in virtual address space also we fix lower memory area for which can map to kernel. So every process would be having some pages which are going to map to same frame number.
Yes, sir.
So every process in kernel mode may have same physical address also.
Yeah, yes, sir. Here they are sharing that
They
kernel
are
code.
sharing. Fine. So this is how paging can help you up. At that time, I told you, just give Just control the page table and you will be able to share. You need not have different copy of kernel at different memory location, because that is waste of resource. No, because kernel is reentrant code. Kernel cannot be written. Okay, kernel can be accessed only. And if there is a need of writing, we have lock and unlock all those procedures. Remember?
By the synchronization mechanism we share, only one
Yes,
process can access.
can access. So just see this slide. So what I'm saying that there are two processes, P1 and P3 and P2, three processes. Fine. Now, process P1, process P3 and process P2, both are using editor program. Both wants to use code of editor, which is in main memory, ed1, ed2, ed3, three editor. एडिटर एक ही प्रोग्राम रखेंगे मेन मेमोरी में, ठीक है, जिसको यूज करना हो, ठीक। 3 पेज हैं एडिटर के, रखे पड़े हुए मेन मेमोरी में। Now, if you see the page table of process P1, ed1 is mapping to 3, ed2 mapping to 4, ed3 mapping to 6. Fine, 3, 4, 6, 3, 4, 6. So if you can play with the page table, we are required to have only one copy of editor, or in our case kernel when I took that example, in main memory. And now you just write down the same frame number in the page table, and in this way pages can be shared. You got the point, Brijent?
Yes, sir.
And how to control that sharing, that's another story. We have already seen process synchronization.
Yeah,
At memory management level, we need to have only one copy of editor in physical memory. Got the
sir,
point?
yes, sir. Frame number is all is stored in the page table of every
और फ्रेम
sharing
नंबर क्योंकि
process.
पेज टेबल में डालना है, वो फ्रेम नंबर हमने सेम रख दिया सभी में, सभी प्रोसेस में. In this way, kernel and all the shareable pages can be shared. Got the point?
Yes, sir.
So, or if you go and see today the process management video where I told you how kernel is shared, मैंने important करके लिखा है slide में. If I can show you the process management slide, let me see. Process XV6 process management. If I can show you, let me. Just a minute. Just a minute. I just want to remind you so that you can go and see that part. See this. Remember how kernel runs. OS code is mapped into virtual address space of every process. Pay attention to reserved in the figure of memory layout. Remember this reserved in virtual address space? Remember Vijendra?
Yes sir, yes sir.
ये reserved हो गया और this reserved virtual space always translate to physical memory where OS executable is loaded.
मतलब सर इसका मतलब ये है कि जितने भी प्रोसेस चल रहे हैं मशीन में
सबके रिजर्व वाला जो वर्चुअल एड्रेस है वो भी सेम है, ठीक है, लोअर मेमोरी में है और वो ट्रांसलेट भी सेम होगा। वो हमेशा ओएस का कोड जहां लोड हुआ होगा मेन मेमोरी में वहीं ट्रांसलेट होगा।
ये सर मतलब ये है कि हर एक प्रोसेस को ये है कि उसका अपना ओएस उसके पास है।
हाँ, सबको लगेगा मेरा ओएस मेरा ही है ओएस, किसी और का नहीं है, ठीक है।
मतलब हर एक प्रोसेस अगर वैसे पूरा देखेंगे तो ओएस भी उसका एक हिस्सा है।
हाँ, ओएस ऑन बिहाफ ऑफ प्रोसेस रन कर रहा है, ठीक है, प्रोसेस वही चल रही है लेकिन कर्नल मोड में चल रही है। इन्वोक कैसे होगा? खाली तुमको अपना प्रोग्राम काउंटर चेंज करना है। प्रोग्राम काउंटर भी लॉजिकल एड्रेस है, वो तुम्हारी प्रोसेस के लॉजिकल एड्रेस में रिजर्व में चला गया, रिजर्व में गया, वो पेज टेबल में गया, पेज टेबल में जहां पे कर्नल एक्चुअली स्टोर है फिजिकल मेमोरी में वो उसको ट्रांसलेट कर देगा और सभी प्रोसेस में यही होगा। इस तरीके से
तो सभी में ये सर
मतलब ओएस का कोड
सिंगल कोड।
ये स्लाइड ही बनाई थी मैंने, ठीक। Are there many copies of OS code in memory, one for each process? No. Virtual address of kernel code in any process points to the same physical address. In this way, processes can share kernel code by having only one physical copy in memory. This methodology is also utilized to share libraries and other large pieces of code also by mapping the library into virtual address space of every process that need to use it. ठीक है?
Yes.
So this is now a right time to revert back to our that thing. So this is how we are going to share the pages. Clear Abhigyan?
Yes sir.
Abhigyan?
Yes sir.
फिर से जाना वो देखना वीडियो, अब इसको फिर से देखना, ठीक?
Yes sir. Yes.
Okay. Similarly, we can share the segments also. Suppose there are two processes, P1 and P2, logical address. Both are having editor segment and their data segment. So you can see in segment table, editor is segment 0, 25286, base is 43062. Here in process segment table of process P2, 43062. Got the point, Brijen?
Yes,
in
sir,
this
yes,
way,
sir.
you can share the segments also. So with this, we have come to the end of memory management. In Intel and in Ultra Spark, there is a concept of page segmentation also, where there are two levels of abstraction. Segment तो different sizes के होते हैं, but उनको भी पेज में डिवाइड कर देते हैं। तो which page of which segment? तो पहले S निकलेगा, so your virtual address would look like this: S P D. Which segment? Which page of the segment? And in that page, what is the offset? So these type of combinations can come in examination. I can give you architecture where virtual address can be divided into a segment, then page, and then within the offset. Or we can have P1, P2D kind of thing. We can have S, P1, P2D kind of thing. Okay. So these type of combinations can be asked in the examination. Got the point? Abhigyan?
Yes sir.
So from my side, only two things are remaining. One is deadlock. Why I have kept deadlock at the last? Because Deadlock prevention, deadlock detection, and everything is not used by any modern operating system until unless you have a real-time system where it is very dangerous to have deadlocks occurring. Deadlock is a classical topic which, apart from operating system, is also required to be understood. For any system development, in any system development, what is a system? System is a machine. What is a machine? Machine is having states and transitions. Is this point clear or not, Brijendra? Any machine is going to have
Yes, sir.
states and transitions.
Yes, sir.
So when you develop any system which consists of states and transition, it should not happen that it ends into a deadlock until unless it is a reactive system which comes back to the start state again. So there should not be deadlock in between that somebody is moving around same states and not moving ahead into the not progressing ahead. So deadlock topic is important not only from the point of view of operating system, it is important from the point of view of any system design. So only one topic is remaining, deadlock and thread. Two topics are remaining from my side, which will be covered. I'll try to cover in the next lecture, both topic, and then my course will be finished. And you will be covering one file system lab class. Okay, Brijendra?
Yes, sir. We will finish that one on Wednesday.
On Wednesday, we'll be having a file system class. And one more information, Abhigyan, just tell to everybody. After the lab class and after I upload the assignment of the lab class, there would be a 1 hour quiz, objective quiz, okay, on Wednesday.
Okay, sir.
Okay, so just be prepared for that 1 hour quiz after the lab class, because lab class will be over in 1 hour. Okay, Brijen?
Yes, sir. Maximum 1 hour.
Maximum 1 hour. So we'll be having 1 hour quiz, objective quiz after the lab class. Okay.
Yes.
So if there are no more questions and no more confusion, then we can leave.
Okay, sir.